Welcome to the Chemistry channel. In our recent video lesson, we talked about the electron configuration, and I promised that I'm going to create series of content giving a practical example on a board on how to write the electron configuration after I use the model to explain the principle governing the electron configuration. So the first example on our list will be the sodium element. So this model here gives us a summary information about the sodium element. We have the symbol here being Na, atomic number is 11, and we've learned that in a neutral atom, the number of protons is equal to the number of electrons. So the atomic number is the same as the proton number. Okay, so this sodium is a neutral atom, so its electron number is also 11. Mind you, it is only so in a neutral atom. Okay, yes, it is only in a neutral atom that the number of protons is the same as the number of electrons. Take note of that. Okay, so we have the atomic weight of sodium also here being 22.989. We have the name, that is sodium, the electron configuration here. Then we have the crystal structure being body-centered cubic. So take note of that. So now let's move on to the board and tackle the configuration practically. Okay, so electron configuration for the sodium element. All right, now we've learned that before we write the electron configuration of an element, an atom of an element, we should first know the number of electrons available. So here we know that it is 11, right? Yes. Okay, so sodium 11 electrons. Now we learned that after identifying the number of electrons available, the next thing is to write the principal quantum number under consideration. And according to Bohr's principle, we've learned that we always start from orbitals of lower energy before those of higher energy level. Bohr's principle says that orbitals of lower energy level are first filled fully before those of higher energy level. If you don't know all these things, there is a link below this video lesson titled the electron configuration. Watch that. All right, so we have 1 as the principal quantum number. Then the angular momentum quantum number will be S, because we are talking about the first orbital. Okay, the first shell and the orbital within the first shell is the S orbital, specifically the 1s. Now, Bohr says the lower energy level must be first filled fully. Now, there is another scientist by the name Wolfgang Pauli who also said in 1925 that each orbital can accommodate a maximum of 2 electrons, and the spinning should be in the opposite direction, spin up and spin down, that is clockwise and anti-clockwise respectively. So this orbital can take a maximum of 2 electrons, so we indicate it here, right? Because we learned that the number of electrons should be indicated on the superscript, okay, the right superscript. All right, so let's proceed. Now, according to Bohr's principle, from the 1s orbital we will move on to the 2s orbital, which will also take a maximum of 2. Then from there we move to the 2p, and the 2p orbital is degenerate, right? We learned that from the angular momentum and then the magnetic quantum number. realize that we have subshells, and each subshell will take 2 electrons each, making 6. Okay, the link to that video is below, so you can click on that and watch it to understand that concept, because this lesson is a continuation of that. So 6. Okay, so 2 2 6 making 10, and the total electron is 11, so 11 to 1. From the 2p we move on to the 3s according to Bohr's principle. So we indicate the 1 electron left. So this is a correct configuration for the sodium atom. Now I want us to write the expanded configuration. This one is a condensed, so let's expand it and see how it will be. Okay, so 1s will take 2, 2x will also take 2. Now we learned that the p orbital is degenerate, right? It is oriented on the x-axis, so we have the px. Also on the y-axis, making the py, then on the z-axis or the z, giving us the pz. Okay, yes. So this will take 2 according to Wolfgang Pauli's. This will also take 2. That will also take 2. Right? Then electrate 1. So from the 2p we move on to 3x. That one will also take 1 electron. Okay, yes. So this is the expanded form. I want to add a last representation, a way that we can also write the electron configuration, which is also correct. That is the box notation or representation. I did mention that in our recent video lesson, that is the electron configuration. So let's see how that is also done. Okay, so we have the 1s, the 2x, then we have the 2p, x, 2p, y, 2p, z, right? Then the 3x. Okay, don't forget we are using the box notation. We draw a box below each of them. Don't forget that the p orbital is degenerate, so their box is 1 together. Then you divide it. This for the 2px, for the 2py, and the 2pz. Then lastly we have the 3x. Okay, so now we know that we have to use spinning, spins to represent the electrons using the Bohr notation. We have 1 electron spinning up, right? The other spinning down, because according to Wolfgang Pauli's, each orbital can accommodate a maximum of 2 electrons, and they must spin in what? In an opposite direction. Okay, so clockwise, anti-clockwise. And when we get to the degenerate orbitals, according to Hans' rule of maximum multiplicity, degenerate orbitals are first filled with electrons singly in what? Parallel, before pairing begins in the opposite direction. So we have 1, that is single spin, another single spin, that is spin up, another, so singly. Okay, they are parallel. Then we start to pair in the opposite direction. So spin down, spin down, spin down, right? Yes, so that is how we filled degenerate orbital. Okay, then we come to the 1x, the 3s rather, we give it the 1 remaining electron. Okay, so this is how we write the electron configuration for the sodium element. And I believe you are practicing and you are following. In case you have any challenge, please don't forget to tell us in the comment section. And below this lesson also, there is a WhatsApp link. You can click on it and we are going to have a fruitful chat. Okay, yes. Before we end the lesson, let me show you another model talking about the quantum numbers from the various atomic orbitals. So we have the magnetic quantum number, okay, telling us the number of orbitals within the degenerates. Then we have the spin quantum number telling us that one electron must spin up, the other must spin down. So spin up, spin down, spin up, spin down. Yes, if the entire electron, the two electrons within an orbital are all spinning in the same direction, it is wrong. I've explained that under the video lesson quantum numbers. The link is below, so you can click on it to get that concept. Also, we have the coefficient in front of the angular momentum quantum numbers. That is the P. You see the coefficient, this the s orbital, right? The s, the px, the py, the pz, the s. All these pz, py, the x, we were able to arrive at them with the aid of the angular momentum quantum number. Okay, yes, and the coefficient is termed as the principal quantum. So the 1, the 2, the 3 is termed as the principal or the primary quantum number. It talks about the shell in question. Okay, then we have the azimuthal or the angular momentum quantum number talking about the subshells. Yes, so if you don't understand this, also watch my lesson on quantum numbers. I've explained it vividly and you understand the concept from there. Okay, so we will end here and the next video lesson will be on the sodium ion, the electron configuration, how to write the electron configuration for the sodium ion, which is a cation specifically. If you don't know what a cation is, there is a video link also below talking about ions, what an ion is, type of ions, the cation and the anion, their explanation and examples as well. Stay tuned.